This section briefly discusses some design tools that you probably encounter. One of them is Spice. There's commercial versions of Spice available, which you're probably well aware, HSpice, PSpice, and others. And what you may not know is many IC vendors and fab facilities do provide Spice netlists for the circuits and devices. Spice performs a DC analysis, so that basically provides you a steady-state solution, and transient analysis and small signal analysis. In general, it's a matrix type technique, and it's formulated for the circuit and it's solved. The equations typically are nonlinear, and iterative techniques such as Newton-Raphson may be used. Here's an example of the circuit elements when they're represented in a matrix form. So we get basically a matrix of branch voltages. Those are the voltages on the branches. A matrix of branch currents. Those are the currents in those branches. A matrix of the impedances, so that's of the element associated with that branch, and then a matrix of initial conditions. So some simple examples: a resistor would have an impedance of RB, an initial condition of 0, and it gives this equation V equals IR, as we'd expect. A capacitor similarly has the impedance of 1 over SCB in the S domain and initial condition of V naught. So this gives us the capacitor equation that's shown below, and basically it's just an algebraic representation of the differential equation in the S domain. In addition to the branch requirements being met, we have to make sure that we satisfy KCL and KVL, and that's given by those two equations associated with the branch currents and associated with the branch voltages, where A is an incidence matrix, and it would be assigning a value of minus 1, 0, or 1, depending if the branch current is entering or exiting that node or not approaching it at all. And we'd end up with a large matrix, which is often called a tableau, which looks something like the following. So when solved, it'll determine the voltages at all the nodes and the voltages and currents across all the branches, or the currents on the branches. So a transient analysis is performed as follows. If the initial conditions weren't specified, a DC analysis is performed. The simulation is broken into discrete time steps, and basically then numerically integrate it to go from one time step to another, at which point in time a technique such as backward Euler method might be used to insert that new equation into the matrix and solve it over and over again until your simulation is finished. Spice supports many different technologies, some familiar ones: CMOS, bipolar, BiCMOS, just to name a few. It also supports different models for MOS transistors, and it also supports transmission lines, which we looked at earlier on. The complexity of the analysis makes Spice simulation unrealistic for really large circuits, because it is an analog circuit simulator, so typically only portions of design are simulated at this level, but it could still be relatively large. Sometimes these techniques may fail to converge to a solution, and at which point in time you may have to adjust some of the simulation parameters needed to get the simulator to run. Here's a simple example. It's not Spice-like, but it is numerical-ish. It's not matrix-like either, though, but it's just a simple RC circuit that's shown over here. And basically what we want to do is numerically integrate to get a solution here. So in this particular case, we'd have a branch current I12, which would be basically the differences on the node voltage V1 minus V2 divided by R, and I20 basically is C dV dt. So if you let RC equal 1, V equal 5, delta T equal 0.1, which is much less than RC, we can start to get a numerical solution just based on simple algebraic equations. And if we estimate the value then at V2 at different delta T's, we'd see at 5 delta T it's equal to 2. And if we were to solve that by any other technique, which is more analytical, we'd see it's 1.96. It's interesting to note that I guess in 2009 Spice turned 36, and the authors did point out in this little article how surprised they were how successful and how useful the simulation tool became. Here's an example of a Spice MOSFET model. Again, this is considered relatively simple, and this would be how it would be specified. So we have an M1, so that's the name of our transistor, with the source, gate, drain, and body contacts. It's NMOS, and these are the dimensions here for this particular device, which have a length of 1 micron and a width of 6 microns. The model for it is an NFET NMOS, and it's a level 2 simulation model. And here would be the default lengths and widths, threshold voltage, VTO, and some other parameters associated with the technology itself, like the substrate doping concentrations and the oxide thickness. This little thing in the middle is the equations that we looked at before, which looks like a current source. It's a nonlinear current source, but those are the equations we sort of derived earlier on. All the rest of this stuff you could associate with being parasitic resistances of the drain, the body drain capacitance, body source contact capacitance, etc. So here's our familiar, gate, source, and drain contacts, and our body voltage. And this basically would be a much more accurate model, and one of the reasons we really don't have any analytical equations for it. If we move beyond an analog level simulation, we'll move up the food chain a bit to a switch level simulator. They're not analog and they're not really digital, but it gives you a relatively accurate simulation waveform, and often it's just a function of the circuit that needs to be tested anyway. So the switch level simulators model the transistors as simple switches, either passing a value or not, so they're on or they're off. And the voltage levels can be modeled to have different states, so logic 0, logic 1, or X being indeterminate, and each state then has a signal strength, and we'll look at a couple examples of that in a minute. But here's some of the strengths and some of the meanings. If it's driven, this strength is assigned to VDD or ground, or input signals, and driven implies that the node is driven by a current source, so that may be a transistor that's turned on hard. Weak driven, this is like driven but slightly weaker. For example, a pull-up resistor will drive a node to a weak driven state. We also have states of supercharged, so this would be where the strength of a node is basically the value stored on the capacitor, and that state was assigned by a driven strength. So it could be a capacitor that was charged up through a transistor which was turned on hard. We'd have charged. This is the strength of a node whose value is stored in a capacitor but whose state was not set by a driven signal strength. So that basically means that it might be pulled up, for example, through a resistor, or pulled up, for example, through an N-type transistor. And then we'd have a lowest level in our trellis when we do the analysis. So we have a simple example where we'll see the different strengths and where they may be found, and these are relatively straightforward. And basically, we can determine what the value is going to be by looking at the highest point on the lattice that has a downward path to the states that are driving that node, and that's what that trellis would look like. But here's some examples. Here we have a resistor which is pulling this node up to VDD, for example, and it'd be a weak one. Here we have a p-type transistor which is turned on hard, so this would be a driven one. Here we have a capacitor sitting out here, and it's pulled up. Previously would have been pulled up if this value were 0. It would have been supercharged to a 1 state. Now this is off, and now we have this supercharged capacitor charging up this capacitor, which is not supercharged but just charged to 1, and it was pulled up through an N-type transistor which was turned on. Here's some more examples for an inverter. Let's say the N FET is on and the P FET is off in this particular case. And in this case we'd have an output here which is D0, which is driven low. So the transistor is turned on hard, and this would be a driven low. In this particular case, when we have both the P FET is on and the N FET is on, we're going to have both of these competing here, so we're going to have it driven to an intermediate state, and that's basically looking at that trellis. We'd say that it's DX, which is D0 join D1, which is this is the highest point which you can get to both D0 and D1. Here's another picture of an inverter. Let's say in this particular case we have both of these turned on. So this would be this would be a driven 1, because the N-type transistor here was only driving from a charge 0. So this will basically be C0 join D1. The highest point in that trellis is D1. In this particular case, the next state is going to go to a weak 1. I guess if it's stored on a capacitor, it'll go to a C1. So there's also a number of commercial switch level simulators. Silos was an early one. It's now been acquired by Verilog. That would have been some time ago. But basically it supported many logic levels, 12 in this case, and had different strengths: supply, driven, resistive, high impedance for each of the 0, 1, and indeterminate state. Had both the transistor level modeling and gate level modeling, although we haven't really talked about gate level modeling yet. And it also supported behavior models. So for gate level simulation, we move up the food chain a little more. We're not just looking at individual transistors, but we're looking at individual logic gates. So the idea behind this is typically more along the lines of functional simulation with perhaps some delay information added. Both Verilog and VHDL supply simulators with their suites of tools that are usually associated with them, and a gate level simulator can typically handle a very large circuit. Now later when we look at adding some faults, we'll see the need for gate level simulation becomes even more apparent. Some other things that you can do to speed up simulation, and this is a gate level event driven simulation we're going to look at. It's basically just the means of speeding up the computation. So if you're only concerned with the digital behavior of a circuit, it's inefficient to solve the entire circuit every time an input perhaps changes. So what you want to do really is set it up such that it's event driven, in which case only part of the circuit affected by the state change is simulated. That improves simulation time quite dramatically. So here's a simple example we're going to look at with some initial states that are shown. We're going to simulate the circuit with the pulses, and basically when something happens we may add an event to an event queue and then evaluate it at a later time. So in this particular case, very simple circuit. These are queued up. These are what we want to simulate, and we want to see what happens. So when A is evaluated, it's going to cause a transition on C to 1 at 1 nanosecond, and then C would have been added to the event queue. B is evaluated, causes a transition of D to 1. It gets added to the event queue, and then the effect of C and D are evaluated, and we get an output E equals to 1. So no new events are on the event queue, so you basically skip to evaluating at 10 nanoseconds, whatever that next event is. So it's basically we just showed the contents of the event queue for the first 2 nanoseconds, and in that case only 5 gate evaluations were needed. 3 caused events to be scheduled, that was C, D, and E, and 2 did not, because there was not enough information to evaluate the gate, and basically that was one of the A transitions and one of the C transitions. Had the entire circuit been recalculated for each node change A, B, C, and D in a brute force manner, 12 gate evaluations would have been required. So there's obviously some benefits that would be seen with scale. So event-driven takeaways, events are scheduled, so for each clock tick the circuit does not have to be simulated. It exploits local change only, so it's basically the influence of the event, and together these provide considerable speed-up efficiencies. And in addition to this, you can also exploit parallelism for speed-up. And at this point in time, we'll take a break.